Welcome everyone. We're going to be looking at 14.2, which is limits and continuity. YouTube graciously noticed I was making a few videos again and sent me a lovely email telling me how I could spice up my channel. And so I don't think they mentioned some ways, but they didn't mention really cute math shirts like this one, how to be a math person. Step 1, do math, any type. Step 2, be a person. So that's what we're doing today. We're all being math people. Let's see here. I'm going to go here to the paper view and check out. And so, like I said, 14.2, limits and continuity. I think this is spicy. Look, I have your homework with little cute sayings. Have you guys noticed that? So this is from Calc 1, just a little bit of a review of, and Calc 2 as well on limits. When we had one independent variable and we had one dependent variable. I'm zooming in just a little bit, and so that's why I'm pausing to get a little better view here. And so the idea is there was just one path to our point. So if we were trying, and I went and labeled this because I realized there wasn't any label on this, and so I went and labeled this 1, and I labeled this height 2, just so we can kind of look at it. Finding the limit meant walking the path, this is the one path that goes through our point, and we would walk that path from the left and from the right, and if our heights were the same from the left and from the right, that was our output, then that was our limit. And so here the limit exists and it's 2. And it didn't make any difference what was happening at the point x is 1 itself. And so that's what this kind of shows here. As I walk the path from the left and the right, getting closer and closer to x is 1 from both sides, the output is getting closer and closer to 2, even though the output is defined to be 3 at exactly the point. But the idea was we were just getting closer and closer. And so the limit existed, and it was 2. And it did not matter if it was defined at the point, or not defined. Well, I guess this is defined at the point, but not defined to be the limit. And the same here. This is getting closer and closer from the left and the right, just that one path. And we're getting closer to the output 2. Whereas here, the limit did not exist, because as I got closer and closer, in this case to x is 2, to closer and closer to x is 2 from the left and from the right, the outputs aren't the same. And so since the outputs, the heights are different, then the limits were not equal to one another. The left limit was not equal to the right limit, and we said the limit didn't exist. So it's a little bit more complicated in 3 dimension, because at any point that you can be on, so that any point that you're on, I'm going to put a point on here. Maybe I should put it in a color. I don't know if my color will really stand up to how dark that is. But any point that you're at, I just put a point there on the grid. There's just not one path that goes through that point. There's infinitely many paths that go through that one point. So if I have this point AB, and it's on the surface, well, I should back up just a second. This point is in the domain, and it's being projected up. And so really, I should say that when it gets on the surface right here, it has a height as well. But we're looking at from that point when z is 0, and then we know we're going to project it up. So if we get really close to that point AB, right, we're going to have to get close to it from multiple paths, and we're going to be wondering, is the height the same? So I'm getting closer and closer to this point, which, this point in XY plane, there's many ways that I can get closer and closer to that point, right? Infinitely many ways I can get closer to and closer to that point. And then I'm asking, as I get closer and closer, are these heights all the same? Are the Z values all the same? Just like here I was looking at the Y values, the output. Is the output the same? This is the formal definition of the limit with the epsilons and deltas, and you can read through it in your book. We're going to focus more on the informal definition. I lost my L here, and so I'll have to add it in there, and I'm going to add it in here for you guys, equals L right here. And so I'm just saying, in other words, so just looking more informally, the value, what this says, what this situation says, the values of the function evaluated at y, which are our z value, approach L, our limit, as ordered pairs on our xy plane approach a point, a specific point, AB, along any path of the domain of F. And so anyway, so we're going to, don't worry, we're going to do some examples. So techniques for finding limits at a point AB. We're going to look at that. The usual limit finding techniques we learned in Calc 1 and Calc 2. Substitution, factoring, etc., etc. We learned a bunch of them in Calc 1 and Calc 2. A new story, though, because we're in 3 dimensions here, if substitution yields 0, 0, and you cannot find the limit, you will not be able to find the limit for every one of the infinitely many paths through the point. But here's something. So even though you can't find the limit through every single path, if you can show that there is 2 paths that have different limits, so this is along a path C1 and along a path C2, and as x, y, the ordered pair is getting closer to AB, and if the limit is L1 and L2, if you can show that, then because L1 doesn't equal L2, if they don't equal each other, then you can show that the limit doesn't exist. And we're gonna be kind of checking that out, things to consider while you're picking paths. Don't worry, we're going to do some examples. Be certain that the point AB is actually on your path. We're going to be checking that out. So if you're like, what does that mean? Wait for it. Try to use paths that make the degree of the numerator and the denominator equal. And then a third approach is to use the Squeeze Theorem to prove a limit, and a fourth approach is to convert to polar. Have examples of each one of those things, and so we're going to check it out. So this first example that we're looking at is just the usual techniques that we learned in Calc 1 and Calc 2. And so that I'm hoping that if you notice that if you substitute in that x is 7 and y is -1, then I get 7 squared plus 7 times 7 times -1. So that numerator there is 49, take away 49, which is 0. And the denominator, x is going to 7, and 7 times -1, and the denominator is also 0. And if you can look at it and you can figure out a way of factoring it or doing any of those kind of things, and so I hope that you're looking at it and saying, oh, well, this one happens to factor. And so if I factor it, the limit as xy approaches 7, -1. I'm not going to lose my limit, but if I factor out an x here, x times x plus 7y divided by, and in the denominator, well, it doesn't factor, so x plus 7y, but you notice the common factor of x plus 7y. So if I cancel out that common factor, now I'm finding the limit as xy approaches 0, 7, 1, excuse me, 7, -1. I don't know why I was going to change to 0, because a lot of them are 0 is why I was going to change to 0 at 7. And so as I get closer, all I have is x here now after I canceled. So this is getting closer and closer to 7. That was just some typical techniques that you knew about in Calc, from Calc 1 even. So this is example 2. Going to look at it. find the limit if it exists or show that the limit does not exist. And so they're starting me out on, hey, there's some favorite paths. First, I would want to verify that if I substituted in, that I have 0 over 0. So if I substitute in, x is 0, so that's 0 squared, plus sine squared of 0 over 2 times 0 squared, plus y is 0 as well, 0 squared. So this is indeed 0 over 0, right? If it turned out lovely, like 0 over 1, then the answer would be 0. Or if it turned out lovely, like 6 over 2, then the answer would be, what did I say, 6 over 2, 3. So, but it didn't. And so now what we're going to do is we're going to go on that second idea on this example of, since it doesn't naturally factor, and the first time I saw this problem, I thought about, well, could I somehow use, sine squared y over y squared? Well, I can't really, the way that it's written, because this is a sum, and so I cannot, in the sum in the numerator, and so I can't just start manipulating the pieces I want. I've got to work the numerator, which means add those together before I can divide anything, if I can't factor anything. So I'm going to try this second approach, which is the trying some different paths. Now you see, never seen that before, and so that's the reason that I'm suggesting some different paths. So I've got 1, 2, 3, 4 paths for us to consider here. And we're going to just give a try to some of our favorite paths so that you can kind of see how that would go. So if I go, and you can call this path C1 if you want, but I don't usually name them. But if I go along, this is the y-axis, which is when x equals 0. So you could say along x equals 0 or along the y-axis. So then what you do is you go and you plug in 0 everywhere for x. Now you want to make sure that when you do this that you're getting close to where you said. So x's are supposed to be getting close to 0, and I'm saying x is 0. So that's good. And so if this was saying that I was getting close to x is 1, and I said, let's let x be 0, let's look at the path where x is 0, that would be inappropriate because I was not getting close to. Or if I asked you right now, with the way that it's written, what if I'm getting close to x equals 1? Well, we shouldn't be interested in x equals 1. We're supposed to be getting close to x is 0. So no, that would not be appropriate. So, okay, I'm letting x be 0. So when I plug this in, I'm going to have my limit. So x is 0. This is going to be 0 squared. That's 0. So I still have sine squared of y in the numerator. And in the denominator, when I let x be 0, I have y squared. And now I have a limit that I'm trying to find that only has y in it because I let the x be 0. And so where am I interested in y going? Y should be going to 0. So y is going to 0. So I've essentially kind of, when I said that I'm going to stay on this path, I've now turned it into something that just has the one variable. And so I can apply the things that I knew about from Calc 2 and from Calc 1. This is from Calc 1, right? That's that property. I'm going to write it like this so that you guys can see that, hey, that's just that special property. I told you guys that the book that I learned out of called it Theorem 7. And even though the book we're using doesn't call it Theorem 7, I still call it Theorem 7. It's that basic property, right? The limit, am I writing where you can see? As whatever approaches 0, and then sine of the same whatever over the whatever equals 1, right? And I called that Theorem 7, but I have that now, right? So as I get closer here, you could even say that I'm squaring this piece here, and the squaring that piece, according to my limit laws, is the same as squaring the limit of that. And as this gets close to 1, and then 1 squared is 1, right? So this is certainly getting close to 1. Then I would want to look at another path. And so these are some of my favorite paths. So if I look along, so I'm going to go right here and I'm going to go along, and y equals 0 is along the x-axis, which is y equals 0. And we're going to do that same story. We're going to do the limit, and everywhere we see y, we're going to plug in 0. So sine of 0 is 0, and square it, you get 0. So in the numerator there, I just have x squared. And when I plug in y is 0, I get 2x squared. And this is y is supposed to be getting close to 0. I'm letting y be 0, so I'm staying on that path that's on the x-axis, right? So the path is on the x-axis, and it's going through that point. It's going through that point as long as I let x go to 0, right? And then it'll be going through that point. And now you notice, well, x squared over x squared can be reduced out. So this is the limit as x goes to 0 of 1 over 2, which is 1 over 2. And now I have found the limit along two paths, the path, the y-axis, and the path, the x-axis, and they have different limits through that same point. And so I basically now can say that because this limit from this path is not equal to this limit, the limit doesn't exist. So I'm going to just say that because the limit from path y-axis does not equal the limit that we got when we took a path from the path x-axis. We can say the limit does not exist. So we did a lovely job on that. Okay, so that was pretty good. So let's try another example here. It says find the limit if it exists, or show that the limit doesn't exist. And if we do a little plugging in real quick, x is 1 and y is 0. So this piece would be 0. That piece would be 0. So the numerator is 0. That's 1. That's 0. So I'm going to put it 1. That piece was 0. Minus 2, right? Because x is 1 plus 1. And so 0 over 0, of course, right? And so no information. And so what I want to do is I want to look at going along some paths. Now, I just want to mention right now that as I'm thinking about going along some paths, if I think about going along the path, the y-axis, that's the first path I used over there, one of my favorite paths when x is 0. I just want you to see that that's not okay. And the reason it's not okay is because where did we have x approaching? X was approaching 1. And so that's the reason it's not okay. And so if x was approaching 0, then I could pick x is 0. So why don't I pick this instead? So this is not okay for me to choose. I'm going to just cross it out. Probably if I was on my test or on my lab, I would use an eraser, but I'm just wanting to make sure that everyone knows that I was saying, hey, that's not okay. And so if I pick along the x equals, so what could I pick if I wanted to pick a value for x? Right, I could have to pick 1. I have to pick along x equals 1. So if I do that, then I get the limit. And I'm putting in x is 1. So 2 times 1 times y. So this is 2y minus 2y divided by x is 1. So 1 squared, 1, plus y squared minus 2 plus 1. And notice I only have y's in here because I replaced x with 1. So yeah, I only have y's in there. And I'm going to be letting y go to, where does y go? Y goes to 0. So y is going to go to 0. So when I clean this up, when the dust clears, so this is along this path right here, x equals 1. My numerator is 0, and my denominator is x squared. So I'm finding the limit as y goes to 0 of 0 divided by x squared. And 0 divided by x squared is 0. So this limit is 0. Okay, now I want to try a different one. And so if I kind of thought about how I did it here, right? So the next thing I said was, let's go along the x-axis. And so if I did that here, so along, and I'm just going to say y equals 0 this time, but that is the x-axis. So if I tried that, so now I'm putting in y is 0. So I get the limit. And I'm going to have, when I put in y is 0, I get 0 minus 0 in the numerator. And in the denominator, I get x squared minus 2x plus 1. And x is going to 0. And just cleaning it up, 0 minus 0 is 0. So the limit as x goes to 0 of 0 over x squared minus 2x plus 1, that's equal to 0 as well. And so because these are equal to one another, that does not show that the limit doesn't exist, or that the limit does exist. That this does not show that the limit exists and is 0, because how many paths are there? Are there just 2 paths? And the answer is no. There are infinitely many paths. And so this is actually no help at all. I have no information more than I had a few minutes ago about this. If they were different, I could say the limit doesn't exist. Oh man, I was working in my yard and I kind of cut up my fingers everywhere. I don't know that I should be showing them, but ow, they really hurt. And so I've gotten no information, even though I've done 2 things. And so trying another path will only be helpful if the other path yields something different than 0. Then I'll be able to say the limit doesn't exist, because the limit is different along 2 paths. So it's not helpful unless it gives me something different. And so I'm going to try another path, and I'm hoping that you're thinking what would be good. I'm going to put it up here, another one that's not good, but I was just thinking about it along, because I was looking at what I had up here as favorite paths along y equals x, right? So would along y equals x be good? And I just wanted to show you so that you can once again kind of see why that's not okay. Because where I'm going, x and y are not the same. It would not be appropriate to say that they are the same and to pick a path where they are the same. And so because they're not, we're going to 1, 0. And so if they were equal to one another, if I was going to 0, 0, this would be fine. If I was going to 5, 5, it would be fine. But that's what is meant by making sure, be certain that the point AB is actually on your path. So this is the path I'm saying, and my point 1, 0 is not actually on this path. And so we want to make sure of that. So we want to pick something along this lines, though, that is on this path. And so I just started guessing, and I kind of started thinking, well, if I wanted to pick something along, so this is no, not okay, not okay, right? Not on path. That's why it's not okay, right? It's not on the path. This is the path. It's the point that's not on this. This is the path, and I'll say point not on the path. That's better. Point 1, 0 not on path. That's more like it. That's more accurate of what I was trying to say. Okay, so if I start saying along and I wanted to say y equals, now if I wanted something similar to x, do you guys agree that if I went x minus 1, then as x's got close to 1, x minus 1, which is what y is getting closer and closer to 0. So I was wondering, would that be helpful? My friend, Professor Leonard, said that if you look at factoring it a little bit, sometimes, like, this is just a wild guess. And I made this wild guess while doing this problem the first time, just trying to pick something on the path. And he said that, if you thought about factoring it a little bit, and of course I don't have any room here to factor that because I've written these paths on here. But if I think about my numerator, so here I am thinking about it, 2xy minus 2y, when I factor out a 2y, I get x minus 1. And he says that if you factor it and you see something like this, that will be something that's good to pick, particularly if that is going to come in the denominator. And I just wanted to show you that if you look down there at that denominator, I know now you're looking sideways, and ignore the y squared, and you have x squared minus 2x plus 1, just looking at the x's and the plus 1, I hope that you notice that factors. So I have y squared, this is the denominator, plus x squared minus 2x plus 1, and I'm hoping that you notice that part factors, x squared we have, plus, and then x minus 1 times x minus 1, right? This is what this factors to be. So he says, hey, that's a good path to perhaps choose. So we're going to choose that path, and we're going to see how we go. Now, we have the choice of replacing, since we factored it and we have x minus 1s, of replacing all the x minus 1s with y, or we have the choice of replacing all of the y's with x minus 1. And so it actually doesn't matter at all. And so you can do it any which way you want. You also have the choice of plugging this into where you factored it as well. And I have to admit that I was feeling too clever for my boots, I think. And so I said, well, it would be a little bit nicer if I replaced all the x minus 1s with y. And so that's what I did. And it doesn't matter. And so your choice on that. So you do you on that. So I said the limit, and I factored the numerator, right? And where I see x minus 1, I'm going to replace it with y. So this is going to be 2y, and then I had x minus 1, so I'm going to replace that with y because that's what I'm letting y be. And in the denominator, I had y squared, right? And then y squared, and then I had y times y, so plus y times y. And where are we letting y go to? Well, we're letting y get close to 0. So if you're saying, could you've replaced all the y's with x minus 1 and then let x get close to 1? And the answer is, yeah, it would be exactly the same. And so it's just whichever one that you notice. I noticed that because all of the x's were involved in x minus 1, that it would just be clever to do it this way. So I did. So when the dust clears here, I'm going to have, this is the limit as y goes to 0 of 2y squared. And in the denominator, I have y squared plus y squared, which is also 2y squared. Do you guys agree? That's y squared plus y squared. 1y squared plus 1y squared is 2y squared. Sorry, I teach a lot of algebra. The limit as y goes to 0 of 1, right, which is equal to 1. And that is helpful. I didn't go down on these. I went downward, and when I went on the side, and I'm sorry, you can do either. And so there I was demonstrating that you can do either. And so now I can use either one of these and say that when I found the limit along two different paths, the path y equals 0 and the path y equals negative x minus 1, I got different limits. So that means the limit does not exist. So the limit does not exist because that limit 0 that we got here is not equal to 1, right? And so the limit we got from this path, so this whole explanation I don't have to have these crossed out parts. Those are me showing you things you shouldn't choose, is my reasoning. Okay, we did a lovely job on that, and we're going to look at finding another one here. This is example 4, and so we're going to check it out. So it says, find the limit if it exists, or show that the limit does not exist. And I would probably be checking a bunch of paths if it hadn't given me the hint to use the squeeze theorem. So I am still going to plug in. And when I plug in, I get 0 divided by 0. And so since they've given me the hint to use the squeeze theorem, I think they're kind of telling me, hey, that if you check a bunch of paths, that you're going to get limits that are equal. And so if you like, you can check a bunch of paths. So you can check the path x equals 0. And if I choose x equals 0, I can see that I'm going to get 0. And if I choose y equals 0, so that'll be 0 in the numerator, I can see that I'm going to get the limit 0 from that as well. And I could probably choose the path x equals y equals x, that path, because they're going to the same place. And when I do that, I can see that I bet you the limit is going to be 0. Here I'm trying to do it in my head over here, but I'm going to use my room here for the squeeze theorem. Oh, thank you so much. That's so nice of you. Look, my fingers are all mucked up from my yard work.
Oh,
and so do you think I could have 2 Band-Aids? Because my fingers really hurt. I think it will make them feel better because I won't be touching things. The water's lovely. Thank you. Okay, so so if I did show, why don't you do that if you wanted, along the path y equals x, and show that the limit is 0. So I want to check out this squeeze theorem idea. So on the squeeze theorem, this is the hints they gave me. 5x squared over x squared is equal to 5, and you can certainly agree that's true. And y squared is a positive value. So if I went and I added a positive value to the denominator of any fraction, and I just want to show you that because I want to convince you of that. So the only way I can convince you of that is with some numbers. So if you had 5 over 1, you guys agree that that's equal to 5, right? And so I'm just changing this into numbers just so that you can see what I'm saying is true. And then now if I said to you, I'm going to add a positive value, y squared is a positive value, right? So I'm going to add something to that denominator. So I'm going to add a positive value 2. Now, is that still going to be equal to 5? Well, depending on what I added, right? It could be equal to 5. So I've added some value. So if I added 0 on there, then it would still exactly be equal to 5. But because I've added a 2, this is 5/3. And 5/3 is not equal to 5. 5/3 is smaller than 5. And that's what this is saying, that if I add something to the denominator, it just gets smaller. And so that's all that it's saying. And the reason the equal is there, so if you're wondering why is the equal there, it's because I could have added any value. I'm going to put it this as y squared, because I want you to make sure that you know that it's positive. I could add any value, and so y could have been 0. And if I added 0, then it would have been equal to 5. So this is true, and this is true. And of course, that's the hint. So we were just verifying why the hint was true. And so think about why this is true. Now, one other thing about this, would you guys agree, by looking at this, by inspection, that the lowest 5x squared divided by x squared plus y squared for all values of y, what is the lowest that could be? Well, I'll ask you this, if you're not sure, when I ask you what's the lowest it could be, could it be negative? And it couldn't be negative, right? Because x squared's positive, x squared's positive, y squared's positive. So if you do a bunch of division with positive numbers, you're going to get a positive. So the very, very lowest it could be would be, what do you think? Can't be negative. Yeah, it could be 0. That's the lowest it can be. So I want to start off here like this. 0 is, and this is in between, 5x squared, x squared plus y squared, and less than 5, less than or equal to 5. Now, the reason we're building this is look what we have right here. That's what we're aiming for. Now, if I just multiplied, I have y. The only thing I don't have here now is y. And if I just multiplied this by y, that by y, and that by y, I'd have to be careful because y could be positive or y could be negative. And if y is negative and you multiply by a negative, you should be flipping the symbol, and so there's something that I can multiply, and this is the suggestion of the book, and that is the absolute value of y. So I'm going to multiply by the absolute value of y. If I multiply by the absolute value of y, I've guaranteed you that it will be positive, and then I will be able to. I guaranteed you that it will be positive, and I'll be able to. I won't have to flip the symbols. So let's do that. So this is going to be 0 times absolute value of y. This symbol, 5x squared, absolute value of y. X squared plus y squared less than or equal to 5, absolute value of y. Now, the other part you guys told me was always positive, and so here's the story of what I'm going to do. So the algebra really bothered me on this problem at first, and so they hand wave it in your book, I have to admit, but I was like, wait a minute here. And whenever you have a value, I'm just going to make it simple. I'm going to call it x squared, and I'm multiplying by the absolute value of y, just so that you know, because this is positive. If you wanted to, you could put it inside, even if it was, you could put it inside your absolute value and not change the value, because this is a positive times a positive, right? And now it's still positive. Because it couldn't be negative, it's okay to put it inside the absolute value. Now, the reason that I'm wanting to do that is, remember this whole other piece we said was positive, right? Greater than or equal to 0. And so that whole other piece, I can put this whole thing, this is 0 over here, inside the absolute value. So now I have the absolute value of what I was trying to prove from the beginning, right? Less than or equal to the 5 absolute value. So now what I'm going to do, and what you do with the squeeze theorem, is you get some inequality. And I think you saw the squeeze theorem more in Calc 2 than in Calc 1. If I'm remembering way back when I taught the Calc 2, way back. Not that far back, but anyway. So you can take the limit. That's kind of how I think of the sandwich theorem or the squeeze theorem, is that after I get my inequality, that I'm taking the limit of all three sides. So when I do that, I'm having the limit as xy goes to 0, 0 of 0. And then in here, the limit as xy goes to 0, 0 of this absolute value thing. And then on the other side, the limit as xy goes to 0, 0 of 5 absolute value of y. And how it works is that these are both going to 0. So if we have an inequality and the two sides are going to the same thing, it didn't have to be 0, but quite often it is with the squeeze theorem, 0. And these pieces are going to 0, then that is squeezing together, because this is always smaller than it and this is always greater than it, and it's squeezing this to have to be 0 as well, right? Have to equal 0. So this is what we've got now, is this, right? So that tells us that the limit as xy goes to 0, 0, and we got this absolute value thing. So we know this is going to 0. And here's what we can do. This is the kind of the clever part of it, I think anyway. The clever part of it is that absolute value around this. it's because we're getting closer and closer to zero. And so that it doesn't matter if y is positive or negative. Everything is then getting closer to zero. Had I been getting closer and closer to a number other than zero, that I might not have been as lucky. But because I might have been getting closer, if I'd been getting closer to one, then on one side getting closer to positive one, and on the other side getting closer to negative one. But one side might be getting closer to negative zero, and the other side's getting closer to positive zero. So both sides are getting closer to zero. So this absolute value, because I'm getting closer and closer to zero, is not needed, and that's pretty clever, I think. And so this just shows that the limit as xy goes to 0, 0. And yeah, they just kind of hand waved that in the book. And I was really broken up about that, I have to admit. And that's going to 0. And I had to really wrap my head around some of the, things about absolute value. So we did a lovely job on that. And this next example to look at, so we proved that limit is 0. If you would have taken multiple paths, you might have started suspecting the limit was 0, but you haven't proved the limit is 0, even if you take infinitely many paths. And so, because you can't do infinitely many paths through that point. And there are infinitely many paths through that point. Find the limit if it exists, or show that the limit doesn't exist. And so they have this limit, and we have this x squared plus y squared, and we have the natural log of the same thing, x squared plus y squared. And the hint is use a polar bear, and its polar coordinates is really the hint, not really a polar bear. And I just want you to remember how to go into polar coordinates. So in polar coordinates, r squared equals x squared plus y squared. Also, so we know that from polar coordinates. Also, x equals r, and x is cosine, right? Cosine of theta. And y equals r sine of theta. So sometimes it would be necessary to use these. On this particular problem, the r equals x squared plus y squared is all good enough. Because x squared is always positive and y squared is always positive, and we're getting closer and closer to 0, but this is positive and that's positive. This is getting closer and closer to 0, but because they're always positive, it's going from the positive side. And so that's the other hint that they make in your book, is that your limit, it's going to be r goes to positive 0. And so, okay, so we're going to check this out. So when we convert this to polar, we're going to have the limit as r goes to positive 0, because this is positive and that is positive. They're both nearing 0, so this is nearing positive 0, a little bit bigger than 0, right? And then this is r squared, and then the natural log of r squared. And I forgot, because I got so excited by the hint, that that you should check that this doesn't work out anyway, right? So this is 0 plus 0, right? So this is 0, and if you multiplied that by the natural log, and as your natural log of something gets close to 0, that's getting close to negative infinity. I hope that you guys remember that. And so this is an indeterminate form. And I got so excited that I forgot to mention that, that first that I thought about plugging in, right? And I have now that same indeterminate form. That's what reminded me of it. Actually, this is getting closer and closer to 0, and this is getting closer, this part right here is getting closer and closer to negative infinity. And yeah, you cannot say that when you multiply 0 times negative infinity, so that this is that indeterminate form, you can't say the answer is 0, because it's not always 0. And you can't say the answer is negative infinity or positive infinity or anything in between. It takes on infinitely many values. We actually did one like this, and we're gonna get an answer that you guys will say, but it came one of the answers I thought it was, but it doesn't always. And so anyway, so that's kind of the story there. So do you guys remember how you could manipulate this so that you can use L'Hopital's rule? Yeah, you can jam that in the denominator. So when I do that, we get the limit as r goes to this, and natural log of r squared in the numerator, and in the denominator, r to the negative 2. And so, hot diggity dog. And then now, as I get close to 0, this numerator is getting close to negative infinity. And this denominator, because r to the negative 2 is really 1 over r squared, and as I get close to 0, this is getting close to infinity. And if you have negative plus or minus infinity over plus and minus infinity, it's okay to use L'Hopital's. So now it's okay to use L'Hopital's. And I abbreviate L'Hopital's LH so that people know what I'm trying to do. So that when someone's grading my stuff, they know what I was trying to apply. And so if I don't know what you're trying to apply, I can't give you part credit on it. And so if all of a sudden you're just writing from here to here, that now I have this is 1 over r squared times, that I shouldn't write it like that. I should write it up and down. Taking the derivative of the numerator, right, that's L'Hopital's rule, times, I have to use chain rule here, 2r. And the derivative of the denominator, negative 2r to the negative 3, right? And so I have the limit as r approaches 0. So I don't stop writing my limit sign, and you shouldn't either, because when you stop writing your limit sign, you're saying that you already took your limit. And it's okay to clean up, everybody everywhere, clean up, everybody do their share. So it's okay to kind of clean this up. When I clean this natural disaster up, this is going to be, I feel like I don't want to mess up my work over there, but I also don't want to do the algebra in my head and mess it up. So this is, in the numerator is 2r over r squared. So in the numerator is really 2 over r. And then the denominator is negative 2 over r cubed. And so this is what we have for our denominator, negative 2 over r cubed. So we're dividing that, right? 2 over r divided by negative 2 over r cubed. Yeah, I'm getting too much on the algebra. I know, I'm sorry. I can't help it. I teach a lot of algebra. Times r cubed over negative 2. And so when the dust clears here, the 2's are going to cancel out. So I get negative of r squared. When I did this problem earlier, that's not what I got. So did I make an algebra mistake right now, or did I make an algebra mistake then? So this was 2 over r. And this was, did I make a mistake on my derivative? No. Negative 2, I agree with my derivative. And so this is negative 2 over r cubed. So it is divided by, and you flip-flop it. I think I made a mistake before. Okay, so the limit as r goes to 0, I made a mistake on my algebra. Ooh, has it ever happened to you? Of negative r squared. And as this gets close to 0, this is getting close to 0. And so I know that you're saying, well, that was what I thought it was going to be. And so this is random. This is a random act of algebra right here. And I hope it's right. Okay, anyway, so our answer here is 0. You did a lovely job on that. Okay, so the next thing that they talk about is continuity, and so they tell us that f is continuous at AB if f is defined at the ordered pair AB, and as the limit as x, the ordered pair xy, approaches the ordered pair AB of f of x, if that exists. So this is like the continuity checkpoint, that checklist that they gave us in Calc 1, and if they're equal to one another. And again, the following functions are continuous on their domain. polynomials, rationals, roots, trig, exponential functions, logarithmic functions, there's a logarithmic function, inverse trig functions, and hyperbolic functions. I felt bad, and I wish that I would have put it in here, but I didn't get it in there, and somehow it got out. And so later on, I am going to have this in here. So if you're watching this video later, it'll be right on your paper. But anyway, I just wanted to show you some that violated those conditions. And just real quick, and I'm zooming in just a little bit on these. And so continuity. So this is our points. Remember, they're in the plane where z is equal to 0. That's my parents. They're needing some bananas from the store, Gatorade, and applesauce. I'll be going to get that a little bit later. All the important things of life, all the things in life that make you feel happy. And so this point, all these points are projecting and creating this figure. But at this particular point, there's a little hole in the graph. And so that's a discontinuity. And what's causing it to be discontinuous is this first one, f. F is not defined at the point. And then this one is an example right here. So here we're actually defined at the point. We're defined to be that height there, but the limit actually exists every path would take you to that height, but they're not equal to one another. And so kind of that same idea. And then here, as we're trying to get close to 0, 0, you notice there's not any points around 0, 0, so we can't approach in to 0, 0, and so the limit doesn't exist because the limit's not there. Okay, so we just so that you can kind of see some there that have some problems. My surface doesn't have problems, continuity problems, because there's no holes in it or anything like that. Okay, so this is a natural log function right here, and it says that, hey, logarithmic functions are continuous on their domain. And so they're asking me what region is this continuous on, and all I have to do is answer its domain, and all I have to do is worry about where x minus y is greater than 0, because that would be its domain, right? Natural log has to, all log functions have to be, the input has to be greater than 0. So that x has to be greater than y, or I like to write it with y first. Y is smaller than x, and so it's continuous on domain, which was the set of x, y's such that y is less than x. So we did a lovely job on that one. And then this one's asking you the same thing. Determine the set of points at which the function is continuous. And this time it has got 3 independent variables. And the only problem I might have, notice the kind of function I got right here is a rational function. And so this is going to be continuous on its domain. And looking at its domain and thinking about it, well, just that the denominator cannot be equal to 0, right? And maybe put the 4 on the other side. I think this is the outer shell of a sphere, isn't it? And so that it's not so the shell of the sphere is it's not continuous on points that are on the shell of the sphere, but it's continuous at all the points inside and all the points outside of the sphere. So this is, because it's rational, is continuous on its domain, and its domain equals the set of x, y, such, z, x, y, z, sorry. If Susie was here, she would have stopped me from that. My little cat, she's really good at helping me with my typos. Okay, so it's continuous on its domain, and that is its domain. And I think that is it. So awesome, 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 awesome. I hope you thought it was awesome too. And I will see you again sometime. Okay, how do I turn it off? Stop recording.